We're going to be talking about LeChateliers Principle, and LeChateliers Principle is what we use to predict what a reaction at equilibrium will do when it's challenged by some sort of change. So let's go over the definition and sort of try to clear up what the definition means. This is a definition. It says, when a system in equilibrium is disturbed by a change, now, two things. The system is in equilibrium and is disturbed by a change. What does that mean? That means it's not at equilibrium anymore. So it was at equilibrium, now it's out of equilibrium. The other thing to think about is change. What do we mean by change? Well, this is going to boil down to rates of reactions, okay? So when we talk about a change, we're talking about something that changes concentrations or changes rate constants. So what kind of things cause changes in concentration? Well, you can add reactants, or you can add products, or you can change the temperature by increasing the system's temperature just by heating it, or you could cool it and change the temperature and cause a change that puts the reaction out of equilibrium. Okay, so we'll go into details of different kinds of changes and how we predict based on this. But it's so back to the definition. When a system in equilibrium is disturbed by a change, then the system shifts in composition to counteract this change and restores equilibrium. What we're going to learn later in the semester is that when a system's at equilibrium, it's at kind of a low energy point. By adding material or taking material out of an equilibrium system, it's no longer at that lowest energy point. One of the really cool things about nature is that it almost always has a way of finding the lowest energy point in a system, and that's what it does when it gets back to equilibrium. So let's look at some of the concepts behind LeChateliers Principle. Okay, so here's what we're doing. We have two reactions in a sense. This is the reaction of NO plus H2 to form N2 and H2O. By two reactions, what I mean is you have a forward rate that's up here and you have a reverse rate that's here. These two are in competition with each other. So let's think about what will happen if I increase the amount of NO that's in the system. Remember, the system was at equilibrium. Now I add NO, which I will often write as a two-bodied arrow like that, a fat arrow. That means increasing the concentration or the pressure of the substance. What's that going to cause to happen to the rates? Well, if you think about it, increasing concentration generally increases the rates of the reaction. This arrow will get bigger in response to that change. The reverse arrow, assuming the system was at equilibrium and you just added the NO, won't get bigger right away, but it'll begin to change as well. But the net effect is that the reaction will take a shift to the right to reestablish equilibrium. That is, NO increased, the rate in the forward direction increases. There's going to be a general shift in the composition of the reaction towards the right. So what does that mean if the arrow goes to the right? That means the concentration goes down for H2, will go up for N2, and go up for H2O. Okay, so let's think about another instance. Let me draw a line here so we can draw another case. Let's say I increased the amount of H2O gas in the system. So that's what I'm going to do like this. What's going to happen to the reaction? Well, the forward reaction isn't going to get any faster. So what ends up happening is the reverse reaction ends up getting faster like this. What does that cause to happen? That'll cause a shift towards the left for the chemical reaction. So N2, if the reaction is shifting left, N2 will have to go down, H2 will have to go up, and NO will also have to go up. Now, if you're doing ice tables and things like that, what does that mean? Well, if the reaction's shifting to the left, that means the right-hand side has the negative signs and the left-hand side has the positive signs. If the reaction's shifting to the right, the left side is negative and the right side is positive. That's in the change box in that center line in the ice table. Let's do another example. Talked about increases, but let's talk about decreases. So let's say I decrease the concentration of H2. So that means this is going down. What does that cause to happen in the rates? That's a little bit trickier to talk about. That's why I saved it for one of the later examples. But when the concentration of H2 goes down, what ends up happening is the top arrow gets slower. That is, there's less forward rate, but the back reaction stays the same until equilibrium composition changes, and eventually it will change as well. And these two arrows will be the same length. The net effect, though, is that the equilibrium shifts in this direction, or the reaction shifts to the left in order to get back to equilibrium. So if the reaction's shifting left, this side's going to increase, this side's going to decrease. Okay, so now H2 goes down, so that means the concentration of NO must go up. The concentration of N2 goes down, and the concentration of H2O goes down. Okay? So in general, the way you work these problems out when you're talking about the change of a single component is the first thing you do is figure out what's changing. Second thing you do is, based on the change and how that affects the forward and the reverse rates, you think to yourself, okay, which direction does the reaction have to go to get back to equilibrium? That is, which direction will the reaction actually run faster and get back to equilibrium? So you determine the direction of the shift. And then the last thing that you do is from the direction of the shift, you predict what happens to all other substances. Okay, so most people, this is the explanation they like the best. That is, if I increase NO, they can from that determine what happens to everything else. Or if I increased H2O, they can from that determine everything else. Some people are a little bit more mathematically inclined, and some students really like to look at equilibrium as really just a mathematical equation. So let me go into that, and although it sounds horrible at first, I think some people will like this better than what I just did. So let's think about the same reaction, the NO and H2 reaction, and write out its equilibrium constant expression. You can rearrange this to get everything out of the denominator. So you have the Kc times the NO squared times the H2 squared equals N2 times the H2O squared. So that's that equation. So in our problem before, we said, well, what happens if NO goes up? Now remember, this is an equality. The left side has to equal the right side. So what are the possible changes that could happen in order to keep that equality being true? Now Kc, this is a constant, so that's not going to change. But you could have H2 go down. If H2 goes down by itself and NO is and there's an increase in NO, the system could still be at equilibrium. If NO goes up, the other thing that could happen is N2 could go up, or H2O could go up, and the system would be at equilibrium. So notice what happened. We're saying that the hydrogen could go down, the N2 could go up, and the H2O could go up. In fact, all of these things happen. If we just go back to the previous slide, you'll see that in fact it's exactly the same as we predicted using our shifting of equilibrium to get shifting of composition to get back to equilibrium. So again, some people like this. It's a mathematical way of expressing LeChateliers principle, but you could really do either one. I do really prefer that you learn the conceptual version before you try to fiddle around with this mathematical version. All right, let's do some additional practice problems. We'll stop and do a real quick quiz here. So the first question says, N2 is removed. So try to predict the direction of the shift, the change in composition as a result of the direction of the shift. Okay? So hopefully you came up with N2 is removed, so that's this. That means the equilibrium shifts in this direction. The reaction shifts to the left to get back to equilibrium. The reaction shifts to the left to get back to equilibrium. If it goes to the left, then H2 has to go up and NH3 has to go down. All right, let's try another one. NH3 is added. That is, I have a system at equilibrium. I add the NH3, it's no longer in equilibrium. First, what's the direction of the shift? Well, looking over here, the NH3 is going up. That means the reverse reaction is increasing, going in this direction. What does that mean? That means both the H2 and the N2 have to go up. Okay, last one. NH3 is removed. So if the NH3 is removed, that is, it's going this way, the reverse reaction rate goes down, but that means the reaction is going to be shifting to the right. As a result, N2 and H2 both will go down. Okay, there's a type of problem is what happens when you change the volume and all the partial pressures of all the gases change simultaneously and in proportion to each other. Just to sort of give you an illustration though, it's not just pressure of one thing, it's pressure of everything. So let's say that you had 0.5 moles of N2 and 0.5 moles of H2 and 0.5 moles of NH3, and let's say it's at equilibrium inside a container that has a volume of 1 liter. Well, we can calculate molarity. Molarity is 1 molar, or 0.5 molar. Let's say I take that same container and I decrease the volume. Pretty simple to do this. You put it in a piston or you just pressurize the container. That's another way to do it with all the substances in proportion. And what happens? Well, remember this is molarity, so this would be 0.5 over 0.5 moles over 0.5 liters. And the same for all of these. This comes out to be 1 molar. In fact, all of them, because they're all in the same container, will increase to 1 molar because the volume is decreased to half. So when we say, oh, in a reaction and the volume changes, what happens to the equilibrium concentrations? Really what you have to think about, oh, the volume's changed, all the partial pressures have changed, but they're proportional to each other. So they're either all going to go up or they're all going to go down. And then the system potentially is no longer in equilibrium, and a shift has to take place to get back to equilibrium. So let me erase what's on the screen here, and we'll talk about that. Okay, so let's say you decrease the volume. What we talked about is that means all partial pressures increase in proportion to each other. So they'll double or triple. If you have the volume, you double the pressures. If you third the volume, you triple the pressures. So we're talking about decreasing volumes. What do you do, or what does LeChateliers principle predict will happen? Well, you notice it's kind of thinking about this in rates. There are more molecules in the reactants than there are in the products. As a result, increasing their pressures increases the rate of the reaction to the right faster than it does to the left. So both the left arrow of the equilibrium expression and the right arrow of the equilibrium expression, that is the one going to the product and the one going back to the reactant, both of them will get bigger as a result of decreasing volume. Rates in general will go up. Okay. So what does that mean, though? Well, in this case, the reaction will shift to the right to form products. Now, it turns out that's a pretty cumbersome way of going about describing this, but it turns out there's a simple way that you can think about this. I have 1 mole of gas here, I have 3 moles of gas here, and I have 2 moles of gas here. When the volume is decreased, increasing all the partial pressures, the reaction will shift in the direction with fewer moles. That is, it's going to go to the right in this problem. So decreasing volume, the reaction shifts to the side with fewer moles. Ooh. In this case, that means shifting to the right. But it could have very easily been a shift to the left if the reaction had been different. Okay. So now what happens if you increase volume? Increase volume. That means all partial pressures decrease. In this particular reaction, they're all going to shift to the left. So the reaction shifts to the side with more moles. So that's how we take care of changing volume and affecting all the partial pressures simultaneously. The last thing to think about is endothermic versus exothermic reactions. That is, what is the effect of temperature on chemical reactions? Now, when we talk about an endothermic reaction, what we're talking about is a reaction where we think of the energy being one of the reactants. That is, if I have my reaction coordinate diagram, and it looks hopefully decent like this, that's my endothermic reaction. This is reactants, this is products, this is the activation energy here. Okay? For the forward reaction, we know that the reverse reaction has a much smaller activation energy. But we think of, well, delta H, this is delta H. In an endothermic reaction, this energy is a necessary component in order to produce the product. So if we add energy to an endothermic reaction, it will cause the reaction to produce more products because there's literally more energy to produce the product. So products will increase if you increase the temperature in the endothermic reaction. But what about an exothermic reaction? An exothermic reaction, when we write it, looks like this. There's the reactants, right? There's the hump, and then there's the products. This is delta H. And we think of the energy as a necessary part of the reaction because this is the energy it has to leave in order to form the products. So I can get more products in an endothermic reaction by adding energy, but in an exothermic reaction I have to remove energy to get more products. So let me write some of these things out. But as you remove the energy, that is, you literally remove E from the system, then more product can be produced because you've removed some of that energy. Okay, so this is this pretty standard argument for how this works. I'll give you a slightly different version in just a second. So reactants plus energy makes product. That's endothermic. That means if temperature goes up, that's my little arrow for increasing, by the way, the reaction shifts to the right. If temperature goes down, the reaction shifts to the left. On an exothermic reaction, if you increase temperature, the reaction will shift to the left, and if the temperature decreases, then the reaction shifts to the right. You notice they're the opposites of each other. But in all cases, increasing energy shifts, that is, increasing temperature, shifts the reaction away from the side with higher energy, and decreasing temperature shifts the reaction or towards the side with higher energy. Okay, so there's other ways to view exothermic and endothermic reactions that help explain LeChateliers principle probably a little bit more accurate. So what I'm going to do is describe this on a next slide, which is really a blank slide. So let me get a blank slide up. So what's the other way that we can think about this? Well, let's think about an endothermic reaction, for example. Here's the reactants, and the energy increases and goes to the products like this. Now, remember, this is the activation energy for the forward reaction, and this is the activation energy for the reverse reaction. And remember that K from the Arrhenius equation is equal to A times e to the minus EA over RT. So for an endothermic reaction, EA is bigger than the reverse reaction. So EA forward is bigger than EA reverse. So what does that mean? That means this side responds to temperature more rapidly. That is, this temperature has a bigger effect on the forward reaction than the reverse reaction. So in an endothermic reaction, when you increase temperature, that causes a disproportionate increase in the forward rate of the reaction, so that the arrow on the reaction arrow looks like this when the temperature is increased, but the reverse arrow doesn't increase as much. Okay? So in other words, forward reaction rate increases, a shift to the right in the chemical reaction. Let's go back through the same argument for an exothermic reaction. Let's talk about what happens when you look at an exothermic reaction. In an exothermic reaction, the reactants are up here, the products are down here, and then we have a big hump that goes in between the two. Now, in the exothermic reaction, that's the activation energy in the forward direction, but the reverse direction now has the bigger activation energy. So EA reverse is greater than EA forward. That means that the reverse reaction is more sensitive to temperature change than the forward reaction. So what happens then is, let's say that temperature goes up. If the temperature goes up, the reaction rate is going to get faster in this direction. And although the forward reaction will get faster, it's outrun by the reverse reaction. And as a result, the net shift of the reaction is going to be to the left. If I lower the temperature, then what will happen is, so this is increased temperature, and this is decreased T, so I can just do that. If I decrease temperature, then what will happen is, let's say at equilibrium the arrows are this long. Okay, remember at equilibrium the arrows are the same size, so we're going to just try to do that at the same size. The reverse reaction rate will go down faster than the forward reaction rate. So I'm decreasing temperature, which means that versus maybe that. The net effect is the reaction will go to the right as you remove energy or lower the temperature of the system. The net shift is to the right. Here's an example. This is an endothermic reaction. How can you change temperature to increase the amount of cobalt chloride that's formed by this reaction? Okay, so think about this. You have a reaction. This is what I think would probably be best for you to do. First of all, it's endothermic. That means energy is on this side. What can you do to make more product appear? That is, you want the reaction to shift to the right. So in order to do that, you have to increase the temperature to push the reaction to the right. So on these kinds of problems, I think the best approach is, one, make sure you understand exothermic and endothermic. Place energy in the reaction. And then, two, depending on what the problem asks, but really what you're always doing is check to see whether or not energy is removed or put into the system for the shift that's desired. So look at the change in E before you try to figure out anything else.